The derivative of a single variable function was defined in your Calculus 1 course. The derivative represented the slope of your function or the slope of the tangent line at a given point. And another way to think of it was that it represented the rate of change of your function with respect to the variable at x equals a. When you've got a single variable function, there's only two directions in which you can get closer to a certain point. Well, when it comes time to talking about multivariable functions, how do we talk about the derivative? When you've got more variables, your function is now defined over a set in R2. And that means there's a lot more ambiguity as far as how should you approach a certain point. Now, to try to give you an example here, we've talked about this function in a previous video. This is what's called a hyperbolic paraboloid. Now, a hyperbolic paraboloid kind of looked like a saddle. If you looked at it with respect to certain traces, it would look like a hyperbola. If you looked at it with respect to other traces, it would look like a parabola. So if we just put in a coordinate system, something like this, we've got our standard x, y, z coordinates. If you cut this in different directions, you're going to see different things. So for example, if we were to take a plane that's perpendicular to this y directions at some constant y equals b, well, this plane is going to intersect the curve. Now, if I was interested in the derivative, that'd be like saying, let's talk about the slopes of the tangent lines. So as I walked along, I would be seeing slopes that changed like this. If I were now to cut this with an x-plane, then I would be seeing a different shape. So then the curve here would have some sort of profile that looked like this. And you can clearly see that the orientation of these tangent lines is very different. So it's different behavior depending on which location I'm in. If I move in the x direction, I'm going to get different behavior versus if I were to move in the y direction. So you see that we need to be more careful when it comes to defining a derivative for a multivariable function. And this is going to lead us to a new type of derivative. So the idea is this: we are going to take a two-variable function, let's say z is f of x and y, and this is a surface in R3. If you've got this surface, what we're going to do is intersect this with the plane y equals a constant. And let's say that y is equal to b just to be definite. So if there's our x, y, and z, if we take this plane y equals b, it'll look something like this. We are now going to get a curve of intersection. So now the curve of intersection is z as a function of x, but b is a constant. So really it's just a function of one variable. So we will discuss the change with respect to WRTX. We're just going to use our Calculus 1 definition. And then we're going to talk about things like the slope of a tangent line. So here's a new notation. So this almost looks like a derivative, except these curly D's are really representing what's called a partial derivative. So this is going to be called the partial derivative of f with respect to x at the point x equals a, y equals b. So what I'm doing is essentially just applying the usual old definition of a derivative from Calc 1. This time, I'm only applying it to the x variable. The y variable is held fixed. Remember, we need two input variables because our function is a function of two variables. Now, this is a number, and this number tells me the slope of the tangent with respect to x at the point x equals a. If we've got our plane again where we've kept y is equal to some constant like this, there's the y-axis. We've got a curve of intersection with the function. What is the slope right at that point? Well, that slope is now this partial derivative. Because this can be a little clunky to write down, we can sometimes abbreviate it. We can put f with a little subscript here. That denotes that it's a derivative with respect to x. So on this picture, I'm going to put this derivative with a subscript fx there. Now, similarly, I can intersect this function with the plane x equals a, and that x equals a is going to be a constant, and then discuss the rate of change of this function in the y direction. So in this particular case, we'll have our surface again. It looks something like this. And now what we're going to do is take a plane that cuts in this x location. So x equals a. There's going to be some sort of curve of intersection here. So there's the curve of intersection. This curve now is some function of a and y. So we are going to define this partial derivative of the function with respect to y at the point a, b. And it's simply just going to be the limit as h approaches 0, f of a and b plus h, subtract f of a and b all over h. And again, this is what's called the partial derivative of f with respect to y at the point y equals b. Now this notation df dy, this is a number, and I should put a and b here, and it represents the slope of the function at the point x equals a, y equals b, with respect to the y direction. If I were to take this x equals a constant plane and intersect it with my function, now I'm interested in seeing how the function changes as I move in this y direction. So the slope here would be the y partial derivative at a and b. So the notation again, if I were to say this, we could use this subscript a, b. Now we can also generalize this. When we generalize it, we can talk about a partial derivative function. So we could have df dx or df dy. These are partial derivative functions. Now, the difference here is that their inputs are variables. Now, of course, you could be a little more precise about how you write this. It would simply just be the limit as h goes to 0, f of x plus h and y, subtract f of x and y, all over h. Now, the idea here is that we are holding this y value fixed as h goes to 0. df dx as a function could be written as fx, xy, could be written as partial derivative with respect to x of f of x and y. Sometimes we will write it as dz dx because z is a variable that represents the output of this function. Sometimes we will write it as d with an x subscript of f of x and y. This represents differentiate with respect to x. Sometimes they even like to write it as d1 f of x and y because x is typically the first of the variables there. All of these things are equivalent notations, and we are going to be using them all throughout the course. Now, naturally, you can extend this to any function that has some finite number of variables like this. So let's say you've got m variables. I could write partial f, partial xi, and all this means is partial derivative with respect to the variable xi. So for example, if I had temperature as a function of spatial position x, y, z, and also as a function of time, I could talk about partial of temperature with respect to time, and this would simply just be the limit as h goes to 0 of this function t, x, y, z, t plus h minus t of x, y, z, and t all over h. You could use this notation, t with the small t there. So how do we actually compute these partial derivative functions? All we do is we apply our Calculus 1 techniques while holding a certain variable fixed. If I need to calculate the partial derivative with respect to x, you essentially just pretend all the y variables are constants, and then you differentiate with respect to x. And if you wanted to calculate the partial derivative with respect to y, you essentially pretend all the x are constants, and then you differentiate with respect to y. So here's an example of a function with 3 variables. If I wanted to calculate the partial derivative with respect to x, that means take an x derivative of this expression. In this expression, e to the yz is a constant with respect to x, and that means I can take it out. So what that'll give me is e to the yz partial derivative with respect to x. This is just the same as taking a single variable derivative, and that's going to give me a 2x, and the convention is that we usually write the constants first and then the function in the order of the variables in which they appear here. If I wanted to take the partial derivative with respect to y, this time y is the variable, so this is a constant. And if that's a constant, I can take it out. Now also remember that the z is a constant. However, there is no rule for exponentials that's going to let me take that out, so I'm stuck. It has to stay in there. Because of that, I now have this expression, and this is where I'm going to need to use the chain rule. So the derivative of e to the something is e to the something times the derivative of the something. The derivative is a partial with respect to y. The z is a constant, so I can take it outside there. And what I'll have is an x squared e to the yz, z, and then a y derivative of y. So I'll end up getting x squared z e to the yz. Now you could do a similar thing for the partial derivative with respect to z. It would look exactly like what we just did for the y partial derivative, and at the end of the day, you could find that you'll get this expression. All that will switch will be the constant. The y would be interpreted as a constant here, whereas the z was interpreted as a constant there.